In this set of examples, I'm going to focus on how you can use factoring to help solve different equations. And the key idea here is all of these equations are going to be situations in which you have more than just an x variable. You're going to have maybe an x and an x squared, or an x and an x cubed, or some combination of multiple uses of variable. They can't just be combined into one variable. If you do have one variable, you should just be able to work backwards and solve. You'll notice in each of these examples I have multiple uses of variables. All right? As I go through this, I'm going to be looking at 5 different types of factoring. These are not the only kinds of factoring. They just happen to be the patterns that we've focused on in this class over the last few weeks. The important thing to understand is factoring is not something in which the teacher just says, I want you to do this kind of factoring, or I want you to do this kind of factoring. Factoring is a process, and you look for each kind of pattern, and you keep breaking down your function until you can't break it down anymore. That's the key. So it's not always going to be a one-step process. The other thing to keep in mind is that a first-degree function is just going to have one possible solution. A second degree, a quadratic, usually is going to have 2 solutions. A third-degree function, which I don't have up here, but I will in a minute, usually going to have 3 possible answers. Be aware that you need to be looking for a factorization that will give that to you. The other thing you want to keep in mind is anytime you do a factorization, your final answer, or at least your final factorization, should be written completely as a product. And if it's written as a sum or a difference, you've got some more steps to go through. So let's look at my first examples. By the way, the different methods we're going to be using here, you always want to check to see if you have a greatest common factor. Second of all, if you have any kind of a difference of squares, there's a nice pattern for working with those. A trinomial that doesn't have a lead coefficient, or rather really has a lead coefficient of 1, basically you can use the FOIL process in reverse. If the coefficient is something other than 1, then you're going to have to do a little bit of guessing and checking. It's still a FOIL setup if it's going to factor, but it takes a little bit more work. And finally, we have factoring by grouping, which I'll talk about a little bit down the road. Okay, first example here, in most of our factoring solving methods, you want to get your equation equal to 0. So I'm going to subtract 9x from both sides. I'm going to have 10x squared minus 9x is equal to 0. And again, first step of factoring, you always want to check and see if there's a greatest common factor. You want to check numbers and you want to check variables, because if you can divide a variable value out, a lot of times you can simplify it down to something that no longer has an x squared, and that's what you're going to see in this case. No greatest common factor other than 1 between the 9 and the 10, but you can divide an x out of both. This is really going backwards through the distributive property, and so I'm going to have 10x minus 9 left inside parentheses. Okay, now it's factored. It's written as a product. X times this 10x minus 9. Because the whole thing's written as a product, if I have this multiplying by this to equal 0, either the first part has to be equal to 0, or the second part has to be equal to 0. And in this case, I have a little solving there. We're going to end up finding out that x is equal to 9/10 when you go through the whole process. So x is either 9/10 or x is equal to 0. Again, really important, keep in mind that fundamental theorem of algebra. That's a second degree function, and we can see that we have 2 possible answers. All right, for number 2, needs to be set up equal to 0. I'm going to subtract 12 from both sides here and set it equal to 0. Okay, so a little bit of adjusting there. There's no greatest common factor. Can't divide an x out of all 3 terms, can't divide a number out of all 3 terms. However, I notice it's a trinomial. And not only is it a trinomial, the leading coefficient is 1, which means we've got a pretty simple FOIL factoring pattern here if it's going to factor. Okay? First 2 positions will be an x. Think about FOIL. Don't memorize, okay? Think about how FOIL works. This thing has to multiply back out to equal the original. In particular, the first 2 positions give you an x squared. The last step of FOIL, your values without variables have to multiply to give you negative 12. And in the middle steps, this outer term gets multiplied by an x. These inner terms get multiplied by an x. Those numbers will be adding to give you that negative 4 there. So numbers that multiply to be negative 12 and add to be negative 4, that's going to be a negative 6 and a positive 2 Commutative property says that can be done in either order. And then if we find our solutions, we need x plus 2 to equal 0, or we need x minus 6 to equal 0. And of course, in this case, that's going to be x equals negative 2. And in this one, that's going to be x equals 6. Second degree equation, you notice we get 2 answers. Third example. Always check greatest common factor. There is a greatest common factor. You're going to make your life a lot easier if you divide out that negative 1. So I'm going to have x squared plus x minus 30 equals 0. Notice, trinomial, leading coefficient of 1. I can do my FOIL pattern from above. It's going to be negative 1 times the quantity. We'll have x's in parentheses here. Product has to be negative 30, has to add to be 1. That's going to be minus 6, positive 5. Negative 1 can't be 0, so we don't get a solution from this part of the product. X minus 6 is 0 if x is equal to 6. And x plus 5 is equal to 0 if x is equal to negative 5. Okay, so my 2 possible solutions here, x equals negative 5, and x is equal to 6. And now, moving on to number 4. Moving on to example number 4, you'll see I have 4x squared plus 7x minus 2 equals 0. As usual, I check for a GCF. There's not a greatest common factor here, so I can't do that. I do notice, however, not a difference of squares, not a regular trinomial, but it's a trinomial with the lead coefficient not equal to 0. So there's a chance that it may factor using a FOIL pattern, but the game gets a little bit more complicated here because now I have a leading coefficient of 4. Okay? Either I'm going to have leading coefficients of, leading values in parentheses here of 2x and 2x to give me a 4x squared, or a 4x and a 1x. Okay? So let me try 2x and 2x. Think about the last step of FOIL. Last step of FOIL, the number in the last position has to multiply by the number in the last position and give me that value right here. The place where you have to be careful is, because we have coefficients in front of the x's, whatever's in this position is going to get multiplied by a 2x. Whatever's going to get multiplied in this position will be multiplied by a 2x, and they get added to give you that value in the middle. Notice, because those x's are getting multiplied by something and then added together, we can no longer say that the 2 numbers add up to be 7. They're getting doubled, and then they're adding up to 7. So you don't have that addition rule that you had before, and that's why this is going to become a guess and check process. So the nice thing here is I don't have a lot of numbers that multiply to be negative 2. Okay? So for example, I can try negative 2 and positive 1. And you check FOIL and you see if it works. 2x times 2x is 4x squared. 2x times negative 2 is negative 4x. 1 times 2x is 2x. And right there I can already see it's not going to add up to 7x. I don't even need to do my last step there before I move on. Okay, so I try something else. Okay, I try the negative 2 over here. Normally you would switch positions, but I have a 2x in both positions there. I could also change signs, but if I change signs, all it's going to do is change the sign of the answer. Okay, so this is a rare case where I only really needed to try one example, and then I can throw that out. 2x and 2x is not going to work. Maybe 4x and 1x will work. Now, you can use a little bit of common sense here. I noticed that 7 is very close to 2 times 4. And I know that I can put a number over here that's going to get multiplied by the 4x to give me something with an x variable. So my thought here is that probably the 2x is going to work better here. So I'm going to put the 2 here, and I'm going to put the 1 here. Okay, remember, first 2 positions need to be multiplied to be 4x squared. Last 2 positions need to be multiplied to give me negative 2. I noticed I need a positive value here. The 4 is getting multiplied by the number there, so I'll put the plus there to get the biggest number being positive, and I'll put the negative number there to get the smallest one being negative. And again, if we check, you'll notice 4x times 4x is 4x squared. 4x times 2 is 8x. Negative 1 times x is negative 1x. Negative 1 times 2 is negative 2. And if you simplify down, you're going to notice you get the 7x in the middle there. That is the correct factorization. Now, again, I knew what the answer was going to be ahead of time. Usually, you're going to have to jump these back and forth between different positions, because right now the 2 is getting multiplied by the 4 and the negative 1 is getting multiplied by the 1x. If you change those positions, they get multiplied by the opposite values. So the positions matter, the signs matter, and you have possible different values that you could have in those first two positions as well. Okay, in general, I figure I'm going to have to make 4 or 5 tries before I get a correct answer. As you do more of these, however, you do start to get a sense for where you can position numbers to multiply against your leading coefficient values to generate the number that you're going to need in the middle. Okay, technically I do need to solve this. By the way, these are a little bit more complicated to solve. You want either one of these to be equal to 0. So if I add 1 to both sides, I get 4x is equal to 1. X is going to be 1/4. Over here, of course, x equals -2 would end up making that equal to 0. So those are my two solutions. In example 5, you go down through the process again. Always start by checking for a greatest common factor. Notice I have 2. I can divide out a 2, and I can divide an x out of both of these. Okay? Notice, by the way, cubed, probably going to have 3 solutions, or at least I should be able to explain why it doesn't if that happens. Notice what I have left in parentheses. It's an x squared of -9. Okay? Still has an x squared in it, which means it may still break down. So, I already factored out my greatest common factor. I check, look, the difference of squares. Okay, differences of squares factor just like regular trinomials. You'll have 2 binomials, basically a FOIL setup. You don't want to lose your 2x though. So your 2x is going to come out here. You got your 2 sets of parentheses. Again, you can use a little common sense here. X times x will give you x squared. You need numbers that are going to multiply to be -9, but they need to add up to equal 0 because you'll notice there's no x term here in the middle. So one needs to be positive, one needs to be negative. That's going to be 3 and -3. Okay, a difference of squares will always have the values in parentheses being the square roots of these numbers, alternating signs. And when you multiply it out, you'll see that you get the same thing here. Notice now, 3 values multiply to be 0. That's why we get 3 solutions. Okay? What'll make 2x 0? Well, 2 times 0 is 0. What'll make that 0? X equals -3. What'll make that 0? X equals +3. There are your 3 solutions to that cubic equation. Number 6. Same thing as before, check for GCF. A 2 comes out, which is nice because I get x squared plus 12x plus 36 is equal to 0. And again, we've done the GCF. It's not a difference of squares. It is a regular trinomial. Don't lose your 2. It's going to factor like a FOIL problem here. 9 times 4 is 36. That doesn't work. 3 times 12 is 36. 6 times 6 is 36. Okay. So that's going to be x plus 6 times the quantity x plus 6. And interesting, it's quadratic. You expect to get 2 solutions. But notice, nothing can make 2 0, so that doesn't get us anything. X equals -6 will make this part 0, but that's also the same thing that'll make that 0 as well. So we actually just have 1 solution. Technically in a college course, they'll say it has multiplicity 2, which just means it shows up as a solution twice. But only 1 solution in this case. And now we move on to question number 7. And here's number 7. Question 7, you'll notice that it is degree 3, meaning fundamental theorem of algebra says probably going to have 2 solutions. In addition, you'll notice that there are some greatest common factors here. So we do get to do our first step. Notice that that greatest common factor will drop this down to a 2nd degree equation, which is exactly what we wanted. So I can take out a 4, I can divide out an x, and that is going to give me 3x squared. 4 comes out once, that'll be plus x minus 2 is equal to 0. Okay? GCF is out, there's not a difference of squares, not a trinomial with a leading coefficient of 1, but we do have a trinomial with a leading coefficient that's other than 1. So it may factor as a FOIL pattern. And again, there's going to be some guessing and checking here. Nice thing, we've got to have a 3x and an x in our first 2 positions. We don't have other options in this case. And not a lot of numbers multiply to be -2. I do notice that when I add the 2 numbers in parentheses here, they need to add up to only be 1, which means this times that blank and this number times that blank basically need to be opposite signs that result in numbers that are very close. So they had to get something very small here, okay? So I'm actually going to, I was going to put the 2 here, but if I multiply the 2 by a 3, that's going to give me 6, which is big, and then you'll have a 1 here, and when you multiply it, that'll give you something small. So I'm actually going to put the 2 up against the x, and I'm going to put the 1 up against that. The positive value needs to be bigger. So 3 times 1 is going to be bigger than 2 times x. So I'll put the negative sign there. Okay, if you check that, you'll see that it really does multiply to be this. Again, a lot of times it takes some guess and check. I've been doing this for a while. You have to think a little bit about where those numbers go. But if you have to, you can just keep moving them until you get it to work out. Okay? There's a distinction between something being hard, which this isn't, and something being tedious, which unfortunately in this case it may be. Notice, product of 3 things equal to 0. Either this is going to be 0, which 4 times 0 is 0, or 3x minus 2 would be equal to 0. Add 2 to both sides, divide by 3. Don't have a lot of room to show that, but there it is. And of course, negative 1 plus 1 is equal to 0. And those are your 3 solutions for your third degree equation. Moving on to number 8, you will notice there is not a greatest common factor because there are a whole lot of numbers here. By the way, third degree, probably going to be 3 solutions. You will also notice that this is not a difference of squares. It is not a trinomial. A lot of times, if you have something with 4 terms or 6 terms with an even number of terms, factoring by grouping comes into play. What do you do in factoring by grouping? Very simple. You group your function into pairs. 2 pairs or 3 pairs if there were 6 terms. And you see if you can factor out a GCF from both parts. Even if there's not a GCF, still factor out a positive 1. In this case, you'll notice I can take out a 2. I can also take out an x squared. So there we go. And that is going to leave me with a 3x minus 5. Okay? Now the second part, notice this is still going to be a sum or a difference. I can take out a 7 from both of these, and I want this to be a positive value, so I'm going to take out a negative 7. Okay? And that leaves me with 3x minus 5 when I do that. Okay? Really, really important here. If you don't have the same value in both sets of parentheses, either you did something wrong or it's not going to factor by grouping. All right? You have to have the same value inside parentheses here. A lot of people think this is factored. This is partially factored, not completely factored. Notice, this only has 2 real terms. We have this value minus that value equaling 0. 0 product property only works if I've written it as a product. So I have to still keep going. But you notice, there's this common factor. Interestingly, going back to step number 1 here, there's a greatest common factor that I can divide out of both parts. I can divide a 3x minus 5 out of this, because it's being multiplied by a value, and I can divide a 3x minus 5 out of this term here, because it's also being multiplied by a value. So I can divide that 3x minus 5 out in front of parentheses, and then I have whatever is left. When I divide a 3x minus 5 out of this term, I'm left with just a 2x squared. When I divide a 3x minus 5 out of this term, I'm left with a minus 7, and this whole thing here equals 0. Okay? You don't have to have square brackets here. I just did that to emphasize that it was what was left from here. Okay? So I need to figure out what makes this equal to 0. 3x minus 5 equals 0. Add 5 to both sides, divide by 3. X is going to be 5/3. 2x squared minus 7, by the way, looks like a difference of squares. Looks like it's going to factor down more, but you'll notice no GCF. It's a difference, but they're not perfect squares. But notice there's only one variable here. Okay, I don't have to do anything fancy. 2x minus 7 is equal to 0. I can add 7 to both sides. I get 2x is equal to 7. 2x squared, divide both sides by 2. X squared is going to be equal to 7/2. I can take the square root of both sides. It's going to be the square root of 7/2. Okay? Oh, by the way, remember there's a positive and a negative square root. So it's actually, x is going to be plus or minus the square root of 7/2. You may want to rationalize the denominator, multiply the top and bottom both by radical 2, and you'll get plus or minus radical 14 over 2 if you need a rationalized denominator. Okay? Again, I was focusing more on the idea of factoring by grouping. But do pairs, take out your GCFs, divide that GCF, the new GCF that you get out in front of parentheses, and you should have those remaining values left. That is how you find your solution using factoring by grouping. And number 9, my final example. As you can see here, you have this horrible looking function. By the way, I'm actually not asking you to solve this one. I'm just going to try to factor this thing. Oh, I can set it equal to 0. We can solve 2. It doesn't matter. Anyway, here's the key. The key is it's already partially factored. And if it's already partially factored, you can see, oh, by the way, looks like there are a lot of terms here. You really just have 2 terms. You have this term and you have that term being added to equal 0. It's not written entirely as a product, so I can't apply the zero product property at this point in time because lots of different numbers add up to equal 0. That doesn't tell me anything. Okay? However, you go to your list of factoring methods, the first thing you always want to look for is a greatest common factor. And we only have 2 terms. So we only have to look at both of these for a greatest common factor, and hopefully you notice I have a 2x minus 5 here. I have a 2x minus 5 over there. Meanwhile, I have an x minus 1 as part of that, and I have an x minus 1 as part of the right side as well. I have 2 sets of greatest common factors that can be divided out, and that's exactly what I'm going to do. So, and notice nothing divides out of 3 and 5, so I can just leave those as they are. So, getting started here, I'm going to factor out a greatest common factor of 2x minus 5. Notice there are 4 of those here. There are 5 in my product here, so I can take at most 4 out of both of these. So it's going to be 2x minus 5 to the 4th power. Okay? I only have 1x minus 1 that I can take out of both of these, so that's also going to come out in front of parentheses. Okay? After I divide those out, I have whatever's left. Okay, so from here, when I divide out a 2x minus 5 to the 4th, it completely knocks that out. It leaves me with the 3. When I take out 1x minus 1, I'm left with 1x minus 1. So I have that there. Okay, I have a plus over here. When I divide 4, 2x minus 5's there. It leaves me with the 5. It leaves me with 1, 2x minus 5. And then when I divide out an x minus 1, it knocks out my only 2x minus 1. Okay, so I end up with a product that looks like this. Still not quite done because I've got stuff inside parentheses here that can be simplified. Okay, so that's going to be 3x minus 3 plus 10x minus 25. And let's see, that ends up being 13x minus 28. Okay, so my final quantity 2x minus 5 raised to the 4th power times the quantity x minus 1 times the quantity 13x minus 28 is equal to 0. Okay, if I solve this, anything that makes 2x minus 5 equal to 0 is a solution. In that case, it's going to be x equals 5 halves. X equals positive 1 would make this equal to 0. And anything that would make 13x minus 28 equal to 0, in this case, I'd add 28 to both sides, divide by 13, and that would be 28 13th. Those are my 3 solutions, all right? By the way, this is, that's going to be an x to the 4th. They give you another 2 x's there. That'd be an x to the 6th. And then we're going to have an x to the 5th over here, x to the 6th. It's going to be a 6th power function. You could expect up to 6 solutions here. However, you'll notice this solution gets repeated 4 times. We actually say that that has a multiplicity of 4, and then we get those other solutions. So in a way, you could argue that there's 6 solutions here. However, 4 of them are repeated, and that's the basic idea. So really just a GCF, which is really just an Algebra 1 concept. Just looks a little bit longer, a little bit more complicated. Still not too bad, though, in the grand scheme of things.